Let us proceed.
Hi, Dr. Sakwa.
Yes, how are you?
I'm fine. Long time.
Yeah, it's long. We've just started the lesson.
Yeah, welcome back,
Now,
Victor. Welcome back.
yes, thank you.
Go ahead.
Now, so we had begun looking at the fast powering algorithm, and we had just looked at the Rust code for one part of that fast powering algorithm. So today we to look at another part, another way of fast powering algorithm. Let me just share where I'm referring to. Okay, so when we left, we had just looked at this example. I was explaining how the code functions. So I used this example to explain how the code functions. Now, there's another example just to emphasize that, but I'll not go through it. This example, 28. You look at it, I've again explained how the code will function to give us the remainder when this value is divided by 313. So how the code will then work out by, first of all, letting the result be 1. Then the base change reduces the base, but this base is already reduced. But of course, when you reduce it, you still get the same thing, 27. If it will have been bigger than 313, you will have seen a different base here. So you divide it by 313 and then write the remainder. So you'll go through this again, this example, just explanation of how that code would work to give us the result. Now, so we said that if you are dealing with very big numbers, again, there is a code for that. And let me show that. Of course, it's just the same code, and I had already explained. You only change where there was U128, you change with the big unit. Just change where there was U64, for instance. You write big unit, and so on. But the code remains the same. Yes, and again, it will still work the same way. So this unwrapped part, the unwrapped part that you're seeing here is just meant to assist where there is overflow. Where there is overflow, that is where the number is bigger than the modulus. And then the unwrapped part comes in to assist with that overflow. That is the only difference. And the other difference is just this where we had U64, meaning 64 bits. And we discovered that this would be a smaller number and we want to deal with the bigger numbers, and then we use big unit. But the rest of the code is just the same. Now, so the one I want to look at is one that combines now. For instance, I have this and this. The code we have already is the one that just dealing with one part, just dealing with the 20 raised to 62 mod 17. But this time I want to add these two. This is mod 17, and also this is 55 raised to 99 mod 17. So the mod is the same. The modulus is the same. So the code will just be the same thing as above, only that we include a few definitions a few definitions so that we have the code running smoothly. But before we look at the code, this example can be done manually. To do manually, you do this part first. And we know how to do this part. And then you do this other part, and then combine the two results. That is what you do if you are to do it manually. And again, if you're using the code, that's what the code will still do. The code will do this part, and then you do this part, and then combine the two results. Now, to do this part manually, we use the first powering algorithm. 3 raised to 1 is 3 raised to 1 is just 3. 3 square is 9. We don't require this. We need to square this part. We need to square this part to get 3 raised to 4, which is 13. Then you square this part. It will be 3 raised to 8. 3 raised to 8. I did so many. You only require 3 raised to 1, 3 raised to 2, 3 raised to 4, and then 3 raised to 8. 3 raised to 8 will be this square, the square of this, which will be 16. But 16 is the same as -1. So it's easier to work with -1 than 16. And so for you to work with the -1, you only need to realize that 62 should be written in terms of 8. 62 should be written in terms of 8. How do we write it? 62 by use of division algorithm. 8 goes there 7 times, and the remainder is 6. So 62 can be written as 8 times 7 plus 6. So what that then means is that if you are given 3 raised to 62, this can be written the same as 3 raised to this, because this is 62. 3 raised to 8 times 7, then plus 6, where you would then use the law of indices to mean 3 raised to 8 times 7 times 3 raised to 6. That times 3 raised to 6. Now, but this part, this first part, we've already discovered that 3 raised to 8 is -1. So it's the same as negative. Let me write it as 3 raised to 8, then raise it to 7. And this other part as 3 raised to 6. So 3 raised to 8 is what we know as -1. So that would be -1 raised to 7. Then times 3 raised to 6. And the 3 raised to 6, we know it. Okay, that is why I was including these others. That's why I included 3 raised to 3, 3 raised to 5, so that I could have 3 raised to 6. That's why I was including that. Although we really don't require it to use when we are using a fast powering algorithm. So -1 raised to an odd number will be -1. And then 3 raised to 6 is 15. So this gives us -15. So the first part, 20 raised to 64, which is the same as 20 raised to 62, which is the same as 3 raised to 62, is -15. Is -15 mod 17. But -15 mod 17 is 2. Is 2 mod 17. Just add 17 to -15 and you get 2. So that part is done. Then in a similar way, you work out for 55 raised to 99. First of all, reduce 55 divided by 17. 55 divided by 17, the remainder is 4. So that means 55 raised to 99, the same as 4 raised to 99, mod 17. And again, you would use the fast powering algorithm. you would use a first paring algorithm. In fact, when you just do 4 square will get 16. 16 mod 17 is the same as -1, so that you don't need even you don't need to proceed. You only need now to use the division algorithm. You need to use division algorithm and write 99 in terms of these two. In terms of that 2, because 4 raised to 2 is -1. What is 99? 99 is the same as 2 times 49 plus 1, the remainder is 1. So that means 4 raised to 99 is the same as 4 raised to 2 multiplied by 49 plus that remainder, which is 4 raised to 2. I need to write it inside the bracket. So this is the same as 4 raised to 2, then raised to 49 times 4 raised to 1, this one. But 4 raised to 2 is -1. So this is -1 raised to 49. Raised to 49. And then this other one is 4. But this is -1 here. -1 times 4, which is -4. So then you combine the two results, but -4 in terms of mod 17 is 13. So when you combine the two results, you get the result, which is 2 plus 13, and that is 15. Now that is if you have a smaller number, but now I have a bigger number, and since I have a bigger number, I want to use the Rust code and see how it works. It's just the same Rust code as above. The first part is the same. The second part is the same. This part is the same. The only thing that I've made some difference is that since I'm dealing with the two numbers, I'm dealing with the 2 numbers raised to some power, a number raised to some power. Let me say a raised to some power m, and I also have b raised to n, and I'm getting the sum of these two. I have to define this. The first base 1 is a, so the base 1 I define it. Then exponent 1 is first power, I define it. And then base 2 for the second number, I define it as b in this case. And then power 2, which is exponent 2, also define it. And then mod, I define it. Now you can see I'm using U128. That means I want to deal with bigger numbers, bigger than U64. Of course, if you want bigger numbers than U128, then you would be using big unit. That's what would be, that is now the change you'll be making. Instead of this U128, you'll be having big unit. And then of course you add some unwrap, just as I explained earlier, to take care of any overlap. Take care of that. So it's just the same code. And then after that, this first part here, base 1, or the first part, the part of base 1 and exponent 1, mod m, is supposed to give us the first result. So we say let result 1 be the one that comprises the base 1, exponent 1, and the modulus. Let result 2 be the one that comprises of base 2, exponent 2, and the mod. And then the final result will be the sum of these two results. And then supposing the sum is bigger than the mod, we want to reduce it again. want to reduce it, divide by mod and write the remainder. So that is what this final part is saying. The final part is saying that add the two results. Then after adding the two results, if they try to overlap to be more than the modulus, write the remainder of what you get on a division by the modulus. So that is what this code means. So just the same thing. I would wish to share the code and we try to run it so that we see that it runs. Okay. Yeah, it is. Are you able to see it? Are you able to see the code?
Yes.
Are you seeing from the start of the function?
Yeah, function mod export.
Okay. I'm using U128. U128. You can change this to U64 if you want to deal with smaller numbers. You can change. You can even change to U32 if you want. We are not using I because we are not dealing with the negative numbers. So it's the same code as before. The only change, the only part that is a difference is here. So you can even have as many as you want. If you want A raised to 20 plus B raised to 30 plus C raised to 50 and so on, just come and continue defining your base 3 and exponent 3 here. Define your base 4 and exponent 4. Define base 5, exponent 5. Then after that, come result 1, define it, result 2, redefine, result 3, define, all the way up to the number of times you want to, what you have and you want to add. And after that, come to the main result. Let's try and run this. Okay, so you can see the result. The result is here. It says the result of this number raised to this number plus this number raised to this other number is mod that is, so it's given here. It's given here, that is the result. So we can change, let's change the numbers. If they become too big, then we will change our U128 to big integer. Let me just try and change this part. I've changed the exponent for the first number. I've also changed the power, now the base. Let me again also change this and change that. Let me change the mod, increase the mod a bit, and again run. This one, what does it say? It does not write. It says the thread panicked. The reason is there is an overflow. What that means is that these numbers are bigger than U128. So that means we will have to change a bit. We'll have to use a code that can run larger numbers. I've reduced the modulus a bit. I want to run again the same thing. Let me again reduce the modulus a bit and try to run. it still will not. Let me reduce this a bit, reduce this a bit, and run. Still will not run. So the numbers, these numbers are bigger than what U128 can handle. Okay. I'm still reducing to a level that our U128 can handle. Okay. Okay, so if that is the case, then we're supposed to change and use the code that will run this. Okay, let me now share the one that I've changed the U128 to the big unit. You can see it, huh?
Yes.
Yes, so this time we want to use big unit. The same code, the only difference is while there was U128, we're using big units, and of course, we import those libraries. Those are external libraries, we import them here. And let's look at the cargo toml and see what is there. Again, we have this dependence. These dependencies that will help us to run those libraries. Okay, so let's try to run this. Okay, so it has given us some result. It has given us some result. Let's try to increase the number a bit. Of course, if the number increased if you increase it a lot, then it may run, but take longer time. Take longer time to run. So we don't want to wait for it until it's finished running. We just want to give it smaller numbers that it will run very fast. Okay, and again, it has given us a result for that. So if you want to use bigger numbers, this is what I said you do. Are you seeing the whole thing up to the end of the unwrap?
We're seeing the main function and let modulus.
Yes. That. Okay, I'm just trying to want to see that I share so that you see the entire screen. Just a minute. Okay, so let me again share. I see the entire screen now, up to where I'm highlighting the unwrap. You cannot see the entire screen, eh?
We can see it, but the highlight is is blocked a bit.
Or the unwrap, you're not seeing the unwrap and then the bracket.
Unwrap, then the bracket. No, we can't see that. We're seeing until print line. The result. After that, we're not seeing. Yeah, we can see till the end of the main function.
Okay. Where I've said print the result, this.
Yes.
So the part I just wanted you to confirm if you are saying is this part that I said will be tackling when there's an overflow, the unwrap part. Unwrap, for example, this function, for this function here, main function, I began with the base, let base 1 be, then big unit, then I come up to unwrap, then there's a bracket. You cannot see up to there?
We can see it.
Okay. So those are the only changes, but the code remains the same. So this part is just to use to ensure that there is no overflow. Like in the other case, there was an overflow when the number goes beyond. The number goes beyond, then there's an overflow. But for this case, it will work with that overflow until, because it, so that we get a result. It ensures that there's a result. So that's how you do fast powering algorithm. And of course, the one I've showed is for smaller numbers. If you want to, okay, it was big unit, so that is for larger numbers. For larger numbers, if you want very huge numbers, then that is what you do. And again, I've included that code in my notes. It's just the same code we've looked at. Now you can try these questions using a Rust program. You can try and work out this. It becomes very easy once you have the program. I want us to look at linear congruence. We'll be solving congruence equations, and again, so that we do that using Rust. And congruence equation is just an equation of this form, where we are supposed to find the value of x. A, b, and m are integers, and m is supposed to be greater than 0. M is supposed to be positive. M is a modulus. So the modulus is supposed to be positive. A and b are integers, could be negative, could be positive integers. So we want to find the value of x. So this such equation, an equation of this kind is what we call a congruence equation, linear congruence. These are linear congruence. Of course, linear because if x is raised to a power, then it ceases being linear. If this x is raised to some power, let me say it's raised to 2, x is raised to 3, then it's not linear. But if x is just raised to 1 as it is here, then these are linear congruence equation. Of course, I'll show a Rust code for linear congruence, and I'll also show Rust code for non-linear congruence equations. Now, so what do we mean by a solution? What do you mean by a solution to linear congruence? What do you mean when you say that, does it have a solution? So a solution to this equation would mean an integer, another integer, which when you substitute for x, when you substitute for this x, then it divided by m will give you b as the remainder. So it's that value which, when you substitute where there is x here, and then the result divided by m, b will be the remainder. So that's why I've said that, and of course that will not be the only solution. There will be various solutions. There could be many solutions depending on the GCD of A and M. It will depend on the GCD of A and M. So the number of solutions will be equivalent to that GCD. If that GCD can divide our B. If that GCD can divide our B. So I've said here, not an equation this has a solution if the GCD of A and M divides B. If the GCD of A and M divides B, then we say that this linear congruence equation has a solution. How many solutions? I've said here, in this case, if D is the GCD, and if D divides B, then this linear congruence has D solutions. In other words, the number of solutions will be equivalent, will be this equal to the GCD. So if the GCD is D, then the linear congruence would have D solutions. The GCD is 10, then it will have 10 solutions. The GCD is 15, then it will have 15 solutions. But remember that that 15 should be able to divide B. If 15 does not divide B, then that linear congruence has no solutions. And that's what I've said here. I've said that this congruence has no solution if the GCD does not divide B. Then we say it has no solution. Now, I've given examples where we have a small moduli. So smaller moduli like this, we can just try the numbers from, for instance, this one. We try numbers from 0, 1, 2, all the way up to 7 to find out which ones are solutions. But this one, it's very easy. But what about if the moduli is bigger? The moduli is bigger, I'll show you how to do that, and then bring in the Rust code. Now let's try this. Of course, the solutions will be part of this. But before that, we have to check what the GCD of 5 and 8 is. And of course, that GCD of 5 and 8 is 1, and 1 can divide 3. So therefore, this equation has one solution. So we just need to test and find out which one of these is the solution, which one of these numbers is the solution. We've already said it has one solution, and you've seen why we've arrived at that. So when you are writing the Rust code for this, that is what you just write. So the Rust code must, first of all, determine the GCD of 5 and 8, and also determine if that GCD can divide the number here. If the GCD divides the number here, that Rust code is supposed to give you the results equivalent to the GCD. Supposed to give you the results, which are the same number as the GCD. But first of all, it must verify. It must first of all get the GCD. Of course, you're getting the GCD using the Euclidean algorithm, which we already learned. So I expect that this code will then be having a part of the Euclidean algorithm to determine the GCD. Then after that, it should determine if that GCD can divide B, and then it will then solve. And solving the equations, it will be using the knowledge of the extended Euclidean algorithm, which we also already have. We even already have the code for the extended Euclidean algorithm. So I'm expecting those two to be there. Another way that I can do that is by use of the inverse. So it will then work out the inverse of 5 in this case, and then multiply the inverse on both sides. So I'm also expecting in some cases to also have, you can have Rust code that have the Euclidean algorithm to find the GCD, and then from there it has a method of calculating inverses and then giving you the results. So we have those approaches. Now, for this first question, we already found that the GCD was 1, and that 1 divides 3, and therefore we have one solution among these 8 numbers. 1 is a solution. So just check 5 times 0. So supposing x is 0, because the question was 5x is congruent to 3 mod 8. So when x is 0, we don't get 3. So that means 0 is not a solution. When x is 1, we don't get 3, we get 5. So again, that means 1 is not a solution. When x is 2, we get 10. 10 mod 8 is the same as 2. This is not 3. So again, 2 is not a solution. Let's try 3. 3 times that would be 15. 15 mod 8. If 8 were to go into 15, we go there once, and the remainder will be 7. And of course, this 7 is not equal to 3. And so 3 is not a solution. So we're just trying, just using trial. What about 4? This will be 20 mod 8. Get 16 from 20, the remainder will be 4. That is not 3. So therefore, 4 is not a solution. 5, this will be 25. Mod 8, that will be 1. In other words, 8 into 25, the remainder will be 1. That is not 3. The same thing to 6. This will be 30. Mod 8, that will be 6, which is not 3, and therefore 6 is not a solution. About this will be 35. 8 into 35, the remainder will be 3, which is what we are looking for. And therefore 7 is a solution. 7 is a solution. So we've used trial. We've used trial, and we've obtained a result. And you can see there is only one result when you try all those numbers. There's only one result. Okay, the other question was 6x is congruent to 3. This was the question. So as we said, we first of all find the GCD of 6 and 9, which is 3. And you can see that 3 cannot divide 4. And that then means that this congruence has no solution. Has no solution. So again, when you are doing your Rust code, you should be able to tell that there's no solution. So you tell it that if the GCD does not divide B, then it must give the result that there's no solution. The GCD does not divide B. So that you also tell it that way. Okay, so I'll not go through all the examples. I'll not go through and just show you. This one was the question 6x is congruent to 8 mod 10. So we want to find the solutions if they exist. First of all, the GCD of 6 and 10 is 2. And again, 2 divides 8. and therefore it has two solutions. It has two solutions. You try numbers from 0 to 10 minus 1, which is 9. And when you do that, you will then get that one solution is 3, and another solution is 8. When you do that. Okay, so you'll go through the other questions just using trial and error. And of course, I've included their workings. Include the workings. I want us to look at when we have a big mod. Of course, when you're using Rust code, the mod will be even bigger than this. Also, this number can be bigger, and the number here can also be bigger. How do we solve this? And this is where now our knowledge of Rust code comes from. Our knowledge of Rust code, first of all, we have to tell the program that using this number A and M, do the Euclidean algorithm, and give us the GCD. So it will do that. It will do that and get the GCD. Of course, we are asking ourselves 53 into that, what is the remainder? And then to go there once, the remainder will be 14. What about 14 to this 53? Go there once and the remainder is 13. What about this 13 into 40? You go there 3 times and the remainder is 1. What about 1 into that 13? Go there 13 times, the remainder is 0. The GCD is 1. Now, after it has obtained the GCD, of course, we've already said, after obtaining the GCD, let it verify that that GCD can divide the number here. If it can divide the number here, let it know that there are results and the number of results are equivalent to the GCD. Let it now obtain those results. But if it finds that that GCD cannot divide B, let it return immediately the result that there are no solutions. Let it return that. Let it return that. Now, of course, after it has found that GCD and after verifying that the GCD divides the B, it will now use the extended Euclidean algorithm to find the solution, find the value of X. We want this X to be positive. Since we want this X to be positive, again, when you're writing that code, and then remember that the result that it gets, let it add modulus. Let it add that. Let it add this modulus to that. If the answer is negative, let it add this result. Mod. So 83 plus negative 7, it should supposed to give us 86. And again, after just adding that, so supposing our mod is M and it has just obtained X, let it add the M. Then the result that it gets, let it again reduce it, mod M. It again reduce it, because sometimes this result may again overlap, may go beyond. If it goes beyond, then let it again reduce it. So that is, I think that is, now where there are several results, like the case we had earlier, where there are several results, then we are telling it that after getting this X as the first result, to get the second result, add M to it. To get the third result, add M to this. To get the fourth result, add M to the and so on and so on. So what we are saying is, if you have X as your first answer to get if this is x, to get x2, you take x1 plus m. To get x3, you take x2 plus m. To get x4, you take x3 plus m, and so on. So where there are several results, it's supposed to give you that. And this number of results should be equal to the GCD. Should be equal to the GCD. So the code is here. The Rust code is here. There are several parts. There are several parts because there will be several parts in this question. The main function, we're just telling us the number A, the number B, and the mod. Just telling us what is your mod. So for this part, what this means is that I have 53x is congruent to 1 mod 93. So that's what I'm just defining here. A is my 53, B is 1, and N is 93. And then it will call for the solve linear congruence. And it will call for this with those values, those parameters, A, B, and N. If there is some solutions, then it will print, if there is some, I've said some solutions, it will print solutions to AX. Now this, I'm using this because of the program I used to type. The program I used to type is not able to read this congruence when you just write it. So I use the equivalent to that is the U2261. So this is I use. So when you are typing for you, if you type this, it will still run. Of course, mine is running with this. That is the equivalent of congruence. The equivalent of congruence. So these two mean the same thing. Now, so if there's some results, then it will read solutions to AX congruent to B mod N R. It lists the results here. It lists if there are two results, it will list them there. If there's only one result, it will just put it there. And then, of course, the first bracket, the second bracket, the third bracket, and the fourth bracket represents those numbers. If there is no result, that is after finding the GCD, it discovers that that GCD cannot divide this number B, then it will is supposed to print the congruence AX is congruent to B mod N has no solutions. That's what it's supposed to do that. Now, so I said it has to calculate the GCD and then calculate this part. We had it when we were doing the extended Euclidean algorithm, and we said that in this case, supposing you are given, okay, this one defines the bits you want to use. Define 128. If you want to use big integers, then you'll be using big unit instead of this. So that means that A is a I64. That means it could be negative or positive. Then B is also I64. That means it could be positive or negative. And then the result is supposed to be also I64, I64, I64. Now, so what is this? What is this? This just means that it's giving us the value of this is the result. So when it's working out the extended Euclidean algorithm, that means extended Euclidean algorithm, you're giving us the value of X. See, if you're given A and B, and then you find the GCD as D. So you're just telling us that the GCD of A and B can be written in terms of A and B. Can be written in terms of A and B. The GCD can be written in terms of A and B. So that is what it's giving us. It's giving us the values X and Y. This is what the extended Euclidean algorithm is giving us. Now, of course, we explained this when we were doing the extended Euclidean algorithm. What is this part? If A is 0, that is supposing that I have A and B, but A is 0, so the GCD of 0 and B will be B. The GCD will be B. The GCD will be B. What is the value of X? The value of X, A is 0. So X will also be 0. And Y will be 1. So that means if you give it two values and A is 0, then it's supposed to return this result. This part is supposed to return this result. So it has, what we're interested in so much is the GCD. That's what we're interested in so much with the GCD. So it will return that. Now, if none of the values is 0, then it proceeds with this and calculates the GCD. Proceeds here. So we just proceed the same way we had explained in the extended Euclidean algorithm. Now, I said it should also have a part for getting the inverse. It should also have a part for getting the inverse if there is an inverse. And if there is no inverse, again, it should tell us that there's no inverse. And you know, if there is no inverse, then that means that equation has no solution. Then after that, it should have this part. This part is the solve linear congruent. That means now find the GCD. After confirming that that GCD divides B, it now proceeds to solve the linear congruence. And then it will print the results. It will print the results. Of course, I've explained the code here. I've explained. Let me just share the code first of all. Then we look at it. Just open it. Okay. So I can now share it. That is the code. Can you see it?
Yes.
So I've defined some numbers. A is a slightly bigger number. And then there's a B here, which is also a big number. Of course, these are not big numbers. We can, if we want big numbers, then you know that we is supposed to change these this I-164 to something else and so on. This is the part I told you that this is, you can type here congruence. Instead of this, you can type that and still work. So mine still works with this, will work with that. Let us run this and see if it runs. It has told us that the solutions to this, congruent to this, mod 7, 13, and so on. Oh, this one has two solutions. It has two solutions. It has listed the two solutions here. So one of the solutions is the one, this one. You can see it, huh?
Yes.
At the bottom, where there's the two solutions. The other solution is this. Let's try to change the mode a bit. Try to increase. Try to increase. Try to increase. And run. See if that will happen. It's saying this what? Let's go see what the error says. The error says the number is out of range of I-64. Let's just make it 128, I-128, and see if it will be within that range. I-128, 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 128. There's another one here to change. 128. I hope I've changed all of them. Because if you forget anyone, then it will, oh, they're still up to, these are very long. In fact, this one I've not changed it. This one, supposed to be 128. It's a very long thing. You need to change it before so that to save on time. 128. If you just forget any of them, it will not run. Oh, I've forgotten there's another one here. 128. Let's move down. Just verify that we've changed all of them. 128. I think we've changed all of them. Let's run. What does it say? Mismatched types. Oh, is there somewhere we've forgotten? The I-128. Just trying to check if there's somewhere I've not changed. Okay, so that will mean that we also change this part. Just include 128, this part, I-128. I think that is what it wants, because I'm not seeing the one I've left out. Mismatched. Oh, there's one here. There's one here. There's a 64 here. There's a 64 here. It's supposed to be 128. That is what was about to give us a lot of work. When you forget one, it will not work. Let's try and run. Yeah, it has now run. does now run. I128 runs and gives us those two. It's just one result. This one has only one result, and the answer is here. The answer is here. It's only one result. Now, let me just show you now the code for the big units, and then we stop there. If we have big integers and we want to, so we're just changing where there's 128 and including big units. Okay, so suppose you want to deal with the numbers which are beyond 128, and you're seeing the similarities in these codes, is that where there's a big integers, we're just using big int, and then there's this part that to take care of any overlap, that part to take care of the overlap, and then you include the imports, these libraries. And then you go to the cargo terminal and where there are libraries, and then again, put the dependencies. Put the dependencies in the cargo terminal. So where there was int, no, U120, I128, we just replace with the big integer, big int. So everywhere where it was, just replace with that, and so on. And then try to run. Then it runs. These are very huge number. Oh, this one has no results. It has no results. So it tells us that it has no results. So it confirmed that the GCD, but this one is for quadratic. This one is for quadratic. It's for quadratic. You can see this is x square is that. Not the one I wanted to share. Quadratic is the next one. Quadratic is the next lesson. That is for quadratic. It's not the one I wanted to share. Let me just share it. Yes, the one I wanted to share is here, but there's not much difference. There's not much difference. The way we write for big integers is just the same way. Now here it is. The one I wanted to share is here. You can see the number I put here is a very huge number. It's a very huge number. And then there's another very huge number here for B. Then a huge number for N. Then the libraries here. Then the cargo terminal here. Let's run this. Yeah, of course, it has no solutions. It has told us that this one has no solutions. But it was able to run. It was able to run, and then it writes that this number times x congruent to this number mod this other number has no solutions. Has no solutions. So that means there's no number you can multiply by the first R and then divide by the mod, and then the remainder becomes what is B here. There's no number. Okay, that is it for today. Thank you.
Thank you very much.
Unless there is a question.